I brought a fun little cobweb diagram today, which is of the following function. F of x is 3.3x x 1 minus x. So it's very similar to the logistic growth that we studied earlier, but with a factor 3.3 in front. Okay, so let's see what happens. We start from our initial point over here, and then we go up, we end up over there, and then we translate the output back to an input, and then eventually we end up here, and then we are over there, and then like this, like this, like this. But then this thing keeps on repeating, right? So there's some cycle going on where you cycle in between these 2 points forever. So this orbit never settles on a single fixed value, rather it alternates between 2 different points. And we can call these points, for example, P1 over here and P2 over there. So we have the situation that if you apply the map F to P1, you end up at P2. And conversely, if you then apply the map again, you're back at P1. Okay, so this is a situation that we're having here. The question is, can you now express the same behavior in terms of the map F applied twice? So think about this for a while and see if you can bring in the map F applied twice into play here. So if you just substitute, for example, P2 here in this equation or P1 back in that equation, what you actually have is that if you apply the map twice to P1, you're back where you started. And likewise, if you apply the map twice to P2, you're also back where you started. So what this thing tells us actually is that this particular situation, which we're going to call period 2 point, this particular situation arises when you have fixed points of the map F applied twice. And these together, they form like a cycle of 2 points that alternate each other. And then you can also extend this to a period k point. So it doesn't need to be 2, but it could also be something that repeats after k times. So then you talk about a period k point of a map F as a fixed point of the map F applied k times. There's a small caveat here, is that the number k here, that should be the smallest possible number for which this is true. This is simply to avoid spurious cases where if you have a function, so if you have a map that gives you a period 2 point, right? Then that same period 2 point will also be a fixed point of the map F applied 4 times and 6 times and 8 times. But we don't call this period 4 or period 6 point. We just take the smallest one for which this is true, and then we talk about period 2 points. Okay, so these period 2 points are fixed points of the map F applied twice. So can we then use what we know about stability theorems to tell us something about the stability of that period 2 point? So think about this. So our stability theorem tells us that we should look at the derivative and at its magnitude. So in our case, we need to look at the derivative of the map of which fixed points we're dealing here with. So that's like F applied twice. So we take the derivative of that map, we evaluate that in, for example, P1, and we look at the magnitude. So just to expand this a little bit, this is of course the derivative ddx of the map F applied twice. So we have f of x, this is the map, and then we evaluate that, for example, at P1, and we take the magnitude. Okay, in order to evaluate this, we need our very good friend, the chain rule, of course. So the chain rule tells us that this derivative is equal to f prime of f of P1. But we need to multiply this with the derivative of the stuff in between brackets here. So this is f prime of P1. Okay, and now we use back the fact that we're dealing with a period 2 point here, so that f of P1 is actually P2. So the whole quantity that we're interested in to evaluate is f prime of P1 times f prime of P2. And if you start the same procedure from P2, you will end up with exactly the same thing. So there's some symmetry here. This is a collective property of the entire limiting cycle and not just of a specific point that you happen to pick in this cycle. So if this quantity is smaller than 1, we're in a stable situation, bigger than 1, you blow up. If it's equal to 1, you need to be a bit more creative. So this is how we can apply the theorem that we know to this particular case of period 2 points. But of course, you can generalize this thing also to period k points. And that's a nice subject for an exercise you can sink your teeth in. But that's in a different video.